Okay, sorry for the little delay. So welcome to today's lecture on which will continue the discussion of superconductivity. So we have learned about the BCS theory and the variational wave function that gives for the ground state and the closely related Bogoliubov theory, which reproduces the same variational wave function and also gives us uh, the spectrum of excitations. And the spectrum of excitations of the BCS state we learned are fermions, which usually should be thought of mixtures of particle and hole-like excitations, which have a gap. The gap is delta, which is exponentially small, much smaller than the Debye energy, and at least at weak coupling. And that's kind of the magic of the BCS theory. Many of its features are insensitive to all the details of the phonon spectrum, precisely because the gap is so much smaller than the Debye frequency. And so at this very low energy of the scale of the gap, the physics in some sense is universal. So you get this Dirac, massive Dirac-like fermion, relativistic dispersion near the Fermi level, and that leads to some precise predictions for delta over KTC that we discussed last time. All right, so we also had a good discussion yesterday morning, and there'll be another discussion tonight at 9 p.m. But any questions? All right, so today we're going to continue the discussion, and really where we want to get to is to, now that we have this theory of a new state of matter, we want to understand why it explains some of the remarkable properties of superconductors. And those properties are, of course, first of all, that there's persistent currents, there's large currents that can flow with zero voltage. And secondly, there can be, there's the Meissner effect, that it's a perfect diamagnet. Unlike an ordinary metal, which is only a slightly diamagnetic, it just tries to expel the flux a little bit. A superconductor, a large enough superconductor, is perfectly diamagnetic. It expels the magnetic field inside the superconductor is exactly zero. And why is that? So that's what we want to understand. We won't have a full understanding of it today. We'll get there. But there's a further step, which is derivation of the Landau-Ginzburg theory, which I perhaps will start and will certainly complete by Friday. Okay. So the essential property of the BCS superconductor, as stated here, is one of broken symmetry. So let me remind you what that broken symmetry is. So in any configuration, any ensemble, grand or grand canonical or canonical, this is how we characterized, let's say, what's called the off-diagonal long-range order of the BCS superconductor, equivalently the broken symmetry. And the word off-diagonal is a bit, outdated. It's off-diagonal because if you're given the many-particle density matrix, or the full many-particle wave function, to compute this correlation function, you need an off-diagonal matrix element of the single particle density matrix. On the other hand, we also saw long-range order for a ferromagnet, where you just look at the spins correlation function. The spins were all aligned the same way, so there's long-range order in the spin-spin correlation function. And there, that's a diagonal matrix element of the density matrix. You just have to put it's off, you just have to put a Pauli matrix. It's off diagonal in spin, but not off diagonal in particle space. Anyway, so we'll just refer to it as long-range order. And this is the property that if you annihilate a Cooper pair at position 0 and then create it very far away, the amplitude for that process will have the same phase. This is angle theta, which is a global angle of a perfect BCS state. And that fact is captured by this 2-point correlation function, that this is non-zero, and this complex number psi naught we call the autoparameter. Okay. All right, so what we want to now think about is what happens in the BCS state when theta is not just a constant. And in fact, furthermore, we won't get to that, may get to that today too. We also want to think about a situation where the gap delta is not a constant. Maybe somehow the pairing varies from point to point because of other perturbations that you apply. Or to put the two statements together, since the gap is the amplitude of psi naught and the theta is the phase of psi naught, the complex number psi naught, we want to vary from point to point. I'll put it another way. We're going to think of the Cooper pair operator as some complex classical field, which can vary from point to point, and the value of that field, psi naught, or the average value of psi c, which is just psi naught, is another thermodynamic variable. So this is something we are familiar with when we do stat mech. When you first do stat mech, you take a ideal gas or a weakly interacting gas at fixed temperature and fixed pressure and fixed volume, and then you say, well, we can describe everything in terms of these few variables out of the 10 to 23 variables you have to describe the system. And then next step, you say, well, let's imagine a situation with the pressure and the temperature and the density vary from point to point. And then you get some equations of hydrodynamic type equations, which describe the response of the system to varying pressure, temperature, and volume density. So what we learn now, and that's perfectly fine for a gas, which has no broken symmetry. But once you have a broken symmetry, then the order parameter, in this case, just the classical Cooper pair condensate, the psi c of R, which will be treated as a classical variable because there's so many particles in the condensate, is another thermodynamic variable. So psi c of R becomes one additional variable we have to keep track of, and also ask about how the system responds to this variable, to spatial variations in this variable. How does the energy and the temperature and the pressure change as you change this other variable psi c? So that's the basic idea, which will take us this lecture and also probably next lecture. So associated with any thermodynamic variable, you often have the idea of a conjugate variable, like pressure and volume are conjugate and temperature and entropy are conjugate. So similarly here, we have to think about what is the conjugate variable to spatial variation in the phase theta, okay? And that conjugate variable is what's more precisely called the helicity modulus, and that's what we're going to introduce in a few minutes. And as will become clear below, the helicity modulus of a superconductor is really very closely connected to to the shear modulus of a crystalline solid. Hence the word, in fact. So helicity means, giving some twist. So twist means change the value of the angle theta. So we're going to twist a superconductor and ask, how does it respond? And it's analogous to shear modulus. So if you take a solid, a crystalline solid, that also breaks translational symmetry because the atoms are in some definite positions in a crystal. And then if you apply some shear strain, then the energy changes in response to the shear strain. It's the energy of shear strain squared times a coefficient, and the coefficient is the shear modulus, okay? So similarly here, we're going to twist the phase of a superconductor and then ask how much does the energy change? And that's really the key property of a superconductor that we need to understand and compute. All right, so before I go there, let's consider an even simpler situation where we have this issue of twisting something. And let's just go to the very simplest model of any kind of thermodynamic phase transition broken symmetry, which is the Ising model. So we just take classical Ising spin, let's say at finite temperature, Ising model of ferromagnetism. So I presume you've all seen some description of the Ising model. They're just a bunch of binary variables and which have a term in the energy that if they're near neighbors, they want to line up in the same direction. And so this has a phase transition in dimensions 2 and above, and we want to be in the low temperature phase where the ground state is all spins up or all spins down, but we can even work at finite temperature where there are fluctuations, but still there's a broken symmetry. The spins are either up or down. Okay. So we take a d-dimensionalizing model at some non-zero temperature, and let's take the following geometry. I just don't have the figures all in this text. Sorry. So this is our configuration. We have, oops. So this is the transverse directions of length L perp. So all of these directions are L perp. And then I have the longitudinal directions. And this is of direction of length L. And then I put the same thing on this side. Okay, so there's my geometry. And furthermore, I'm going to take periodic boundary conditions along the transverse directions. So that means that along the transverse direction, this side is coupled to that side. Try to draw that somehow. So this side is the same as that side. So whatever the spin is doing on this plane out here, whatever we're doing out here, you're also doing in the back plane. So everything is kind of trivial in the transverse direction. We are interested in what happens along the longitudinal direction. Okay, and there are d-1 transverse directions. Okay, so that's our geometry. So imagine pretty soon we're going to put a superconductor in this geometry. For now, let's put an Ising model in this geometry and ask what happens at low temperatures. Okay, so what we're going to do is we're going to put a magnetic field and apply it to the spins on the boundaries. So on the left boundary, I'll put a magnetic field H1, and on the right boundary, I'll put field H2. So that means here, if I take the right there. So on this, just on this plane, there's an external magnetic field H1, and just on that plane, there's H2. And there's no field in the inside. So the inside has a full symmetry between up and down, but just right on the boundaries, on just one layer of spins, I put a field. Okay, H1 on one side and H2 on the other side. So now if H1 and H2 are the same direction, let's say they're both up, then the situation is obvious. What the system is going to do, it's going to pick the up state. All the spins will point up, and that will be the ground. There'll be a unique global ground state. It'll just point up because the boundary perturbations have both decided that the spins should point up. And in the low temperature phase, the boundary perturbations have a huge effect because it's, as far as the bulk is concerned, it doesn't care if it's up or down. So if the boundary case is up, well, the boundary wins because the bulk doesn't care. All right, so that's the easy situation. But now let's imagine that we twist the boundary condition. So on one side, we make H1 equal to minus H2. So if I look here, I take a situation where there are spins, and the spins are, on this side, they're going to point up, and on that side, they're going to point down. So what's going to happen now? Well, there's a tension, and this tension means that there must be a domain wall somewhere in between. So there'll be some domain wall which will settle down somewhere. It might fluctuate a bit, but we don't care. We're just solving the problem exactly. And so we might expect there's some domain wall at finite temperature to fluctuate. but at zero temperature, of course, it'll be rigid. So there'll be some domain wall somewhere. Some wall here. So this is a domain wall. Okay, and now the spins on one side are pointing down. So on this side, they're down, and on this side, they'll be up in the bulk. All right. So now let's imagine I can, I'm all powerful. I can just compute the partition function of this theory exactly. And I take the log of the partition function, even with these boundaries, and I just compute the difference in the free energy. So I compute this quantity here, which is the difference in the free energy between anti-parallel and parallel boundary conditions. Okay. So really these two free energies, the models are exactly the same. The boundaries are exactly the same. All I do is I flip the field on one boundary. So, all right. So that's the only difference. All right. So now I ask for the change in free energy. Now the free energy itself, the total. I'm talking here about the total free energy, not the free energy density. That's proportional to the volume of the system in general. So this term has a volume term. This has a volume term. Now, when I take the difference, I'm going to get some surface terms. I have to worry because the volume term is going to be the same. But there are three surfaces I have to worry about in principle. There's the surface over here. There's the surface over there. And then there's the domain wall. Now, the point is, because of the symmetry of the problem, in the two cases, in this case and that case, what happens at this surface is the same as that happens at the other surface, because all we are doing, well, we are only flipping the other surface. So nothing changes here. Here, something does change. I flip H2 minus H, but H2 minus H is a symmetry as far as this surface is concerned. So the free energy, if I just look at this region here, whether H is up or H2 is up or H2 is down, doesn't matter. It should be the same. So in fact, this surface doesn't matter either. So the only surface that matters is this one. So there should be some free energy cost that's proportional to the surface area. Okay, so the change in free energy of the exact free energy will be proportional to that surface area. Okay, so that's something so it'd be L perp to the power of D minus 1. Okay, so delta F is going to be equal to, well, let's say it's equal to, I just realized that in the notes I've written it the opposite order, but anyway. So delta F is equal to L perp to the D minus 1. And the coefficient is it's a positive contribution proportional to the surface. So F, is of order L perp to the D, it's huge, L. So this is L is going to infinity, F itself is really large. But we're not interested in F, we're interested in delta F, the first correction. And that's going to have a term which is, so of course there's various contributions here, which will be proportional. And there'll be a constant here, which will have units of energy divided by L perp to the D minus 1, plus various other terms which are smaller. So this quantity is what we call the surface tension. And in fact, it's the precise definition of what surface tension is. I'm sure you've heard that term before, but this is the surface tension. The extra free energy cost per unit area of an interface between, in this case, up and down spin. Okay, so that is the answer in the low temperature phase, that there's a surface tension and goes to L perp to the D minus 1. Suppose I did the same experiment in the high temperature phase. Well, what will happen in the high temperature phase? In the high temperature phase, spins don't care whether you put a boundary field up or down. The spins are fluctuating a lot. And within some distance of the boundary, what happened at the boundary will be forgotten. The boundary only affects things for some length scale, and then whether you put an upspin or a downspin of the boundary makes no difference because the spins are fluctuating. And in the bulk of the sample, it'll totally forget what the first boundary did. So if you think about it further, at high temperatures, what you then expect is, of course, there's a contribution of proportional to the surface area, but it'll be exponentially small. It's e to the minus L. So that's a much, much smaller contribution because the L goes to infinity. So C is finite. This essentially goes to 0. Whereas at low temperatures, there's a constant. So the exponentially small term is replaced by a constant. And that's the surface tension. Okay, in fact, you could almost view this as the definition of a phase transition. We don't have to, the nice thing about this definition, it doesn't involve any correlation function you have to measure. You don't have to define, even know that there's an order parameter. You don't have to do any of that, or a broken symmetry. You just take untwisted and twisted boundary condition, look at the free energy difference, and see how the free energy scales in the limit as L goes to infinity. If it vanishes exponentially, you're in one phase. If it doesn't vanish exponentially, you're in the other phase. Sorry. Yeah. So one phase it vanishes exponentially, other phase it doesn't. Okay, so hopefully that's telling you something you already know, but in a more formal way. Okay. Any questions? All right, so now we do the same thing, but let's take just to step one step at a time. Let's take a ferromagnet, but not an Ising ferromagnet, where the spins can only point up or down. But let's take a ferromagnet that, because of some spin orbit effect, the spins like to lie in a plane. So this ferromagnet has an order parameter, which is an angle theta. Of course, that's the case for a superconductor too, but just to keep life simple, let's take an XY ferromagnet. That's what this is called. So it's characterized by some angle theta. And in the ferromagnetic phase, it doesn't matter which direction there's a ferromagnetic moment, and it's labeled not by just, there's not two possible states. There's an infinite set of states labeled by the orientation of the angle. All right. So our variable in the partition function is an angle at each point of space in each x and x perp, the longitudinal and the transverse directions. And now we apply a field on the left boundary and the right boundary. But the fields have the same magnitude h, but they're different angles. So let's go back to this picture now. Basically, I don't want to redraw the whole picture. So let's get rid of this. The spins now can point in at any angle. So it's really a continuous symmetry rather than discrete symmetry that goes for the Ising model. So here, let's say the field is pointing in this direction. This is h. And over here is pointing in this direction, h. And this angle we're going to call capital theta. So now this is literally a twist. The spins like to, and theta is a small angle. Of course, it's obvious that the answer should only depend on theta mod 2 pi. So we just take the smallest value of theta mod 2 pi. You point the spins in this, in this direction here, and then at some angle theta, anyways, yeah, on the other side. Okay, this angle theta. So in terms of the twist by an angle capital theta, and so in terms of the Hamiltonian, there's a cosine term on this side, and it's cosine of theta minus the angle theta on that side. Okay, and now we look at the free energy difference as a function of the angle theta. All right, first of all, in the high temperature phase, it's exponentially small, so we don't even forget about that. What happens in the low temperature phase? Is there a contribution which is which looks like this, the constant times L perp to the d minus 1. That's what you get for the Ising model. It turns out there isn't. That's too large. So what's going to happen? So if you suppose what the spins did was have a very sharp domain wall, which is what happens in the Ising model. It had to be sharp because they're the, so this average angle of the spins now I'm going to draw the spins, not the field. So here's a different color. Suppose the spins just, pointing in that angle here, and then there was a sharp bend. Okay. Then there'll be some energy cost at the boundary here, over here, and you would get a surface tension. Okay. But is that what the system's going to do? Well, it can actually, no, it doesn't. That's too much energy. It can lower its energy, and it can lower its energy by not having a sudden twist, but having a gradual twist. I mean, that's what happens, right? If you just imagine a bunch of, bunch of pendulum connected to each other, if you twist one side, they just very gradually twist. Or even in a solid, when you apply a shear strain, the strain doesn't go to some grain boundary and suddenly jump. Well, it could eventually, the strain is very large, but initially when you apply a shear strain, the stress is uniformly spread. So what the system will do, rather than having a sudden twist, it will have a gradual twist. That'll lower the energy the most. So you get rid of the sudden twist, and what you want to do, let's draw the boundary back in. Well, in fact, the boundary won't be there. So what you want to do is now slowly twist from here to there. So very slowly you'll go down. And so what you can see here is that in this region, there'll be a gradient in the angle theta. So the average gradient in theta, and the gradient in the x direction will be the twist that you applied divided by the length of the sample. So locally, there'll be a very weak twist, and it'll be spread out through the entire sample in some way. And that's going to lower the energy. It's going to lower the energy, but not make it exponentially small. That's the difference. So even with a continuous symmetry, there is a phase transition because there is a high energy cost. If you went above the critical temperature, then the energy cost for a twist is exponentially small in L. This is not exponentially small. It'll be small by some power. So the gradient is 1 over L. And so what is the energy cost of this twist? So here's the answer that we need. First of all, it's proportional to the transverse surface area. No problem with that. So locally, you have, what should matter then is the gradient of theta of your angular field of the XY model. So the gradient of theta is some small number, and what you expect that the energy should be proportional to the gradient of theta squared. And that's also true in a solid. The energy is proportional to strain squared. It can't be proportional to the gradient alone because plus gradients and minus gradients are the same. So it's got to be this, and the gradient is very small. So if you do an expansion, the leading term is gradient squared. So you get an expression that locally the free energy density is proportional to the gradient squared. And then you have to multiply the total length of the sample, of course, that's L. Okay, so what you see now is that there's a contribution which is proportional to L perp to the d minus 1 divided by L. Okay, so in the Ising model, it was just L perp to the d minus 1 with nothing. Here is L perp to the d minus 1 divided by L, as L and L perp go to infinity. But that's still much, much larger than what happens at high temperatures, where it's exponential. And that's true for whether it's XY or Ising or not. So even for the continuous symmetry, there can be a phase transition, and there can be two phases. There's the analog of the surface tension is now this coefficient. which I'm calling rho sub s, which is the helicity modulus. And just by looking at this, since theta is a dimensionless quantity, this has dimensions of energy, and just counting dimensions, this helicity modulus in all systems has the dimensions of energy to the length the 2 minus d. In particular, in 2 dimensions, it's just an energy, some, electron volts or something that you have to figure out. So, so that's now in the textbook, and in fact, many, many books. There's what I view as an unfortunate tendency to use the symbol rho sub s, something they call the superfluid density. And they use units of density to talk about it. I really wish they wouldn't, because it's not a density. It's some quantity with these dimensions. And the origin of that, of course, has to go with, if you consider weakly interacting Bose gas with Galilean invariance, then rho sub s has some simple connection to the density of electrons or the density of Cooper pairs. But in many situations in the real world, you're not close to that limit, and then it's not useful to really think about density. But the book still calls it that, and so I'm just warning you. But I'm going to stick to what I think is the right way to do it. Okay. All right. So this quantity is going to determine rho sub s is going to determine all the key properties of the superconductor. So at some point we should be able to compute it from the BCS theory. If I give you a wave function, I should be able to twist it and figure out what is rho sub s. Okay. So any questions so far? All right. So now what we want to figure out now is what happens when you apply a magnetic field? Now, if you were working in the original BCS theory, that's a pain in the neck. You'd have to put the magnetic field in your Hamiltonian and really redo everything. But what we'll see now in this way of thinking, just gauge invariance tells us almost everything we need to know. Okay. So first, let's rewrite this in a different way. In fact, the way we computed it by just taking the gradient of the local phase gradient. So now we can imagine other situation where there's a local gradient in the angle, in the spins, the angle theta, but it's not uniform. It could be anything. Okay. And so then the energy cost, just from this definition of rho sub s, what we know is that if we somehow, for whatever reason, have some gradient of theta, where now I'm thinking of theta as a classical variable characterizing the superconducting state. It's just a parameter in the BCS wave function, but I take it to be a function of r, but a slow function of r. So as long as it's slowly varying as a function of r, the energy should just be an integral over the gradient squared. And the coefficient is the complete analog of the shear modulus, is now the helicity modulus, which is rho sub s. So in an elastic solid, this would be the gradient of the atomic displacement squared, and the coefficient would be the shear modulus. Here is the gradient of a dimensionless angle squared, and the coefficient is the helicity modulus. Okay. And this rho sub s is strictly non-zero below TC. And above TC, rho sub s equals 0 for t greater than TC. It's strictly 0 for all t greater than TC. So there's a sharp distinction in the value in the two phases. Okay, so now what happens? Suppose now I want to know, I call this the effective Hamiltonian, which is meaning that I've forgotten about all the electrons. I'm just characterizing the entire system by temperature, volume, and gradient of theta. So I'm just kind of doing thermodynamics. All right. So how about if I apply a magnetic field? All right, so now we really have to talk about superconductors. Of course, I went through this argument for an XY ferromagnet, but the same argument applies to the BCS state. And where the theta is just the phase of the Cooper pair operator, right here. Okay. We'll worry about the amplitude soon enough. when we do Ginzburg-Landau theory, which may be by the end of this lecture. Let's see. No, probably not. So now we have to figure out what happens in the presence of an external magnetic field. Now, it turns out you can figure it out because in an actual superconductor, this theta itself is not even a well-defined quantity. It's gauge dependent. And you know that because you know that in quantum mechanics, once you have an electromagnetic field, even the wave function is not a gauge invariant quantity. It has transforms under gauge transformations. So we know in second quantized representation, that gauge invariance is represented by this. You take the annihilation operator rather than the wave function, and under a gauge transformation, it acquires a phase. This chi is some arbitrary function of R, which is performing the gauge transformation, which takes the vector potential from here to there. It's sufficient for our purposes right now to worry about time-independent gauge transformation. You can also put in time-dependent gauge transformation, and that can be important for some things. Right, and this coefficient here, E over H bar C, you have no choice but to fix that. There's no arbitrariness in it. And I'm sorry here, CGS units. In MKS units, the C wouldn't be there. Okay, so at least here, the following discussion, just drop the C when you're using MKS units. Okay, so now the Cooper pair operator is a pair of electrons. It's psi up times psi down. So psi Cooper pair will have basically the same gauge transformation, but with a 2. Okay, if you just look at the definition, you see this works. This is the center of mass coordinate now, and it's going to transform the 2. So this is the key, that there's a 2 over there. All right. And so therefore the theta under a gauge transformation has this transformation. Okay. Whereas the vector potential has this transformation. So now we're almost there. This effective Hamiltonian is what we have deduced in the absence of an electromagnetic field. Now we apply an electromagnetic field. This term should still be there, but it should be gauge invariant. It can't possibly not be gauge invariant. So what's the most simplest gauge invariant generalization of this, of grad theta squared? Well, just by looking at this and this, you can see it's this. You just have to add a 2e over h bar c a squared. So in a sufficiently slowly varying magnetic field, for now even assumed to be time independent, if I want to do a thermodynamics for a superconductor, I have to allow for a spatially varying theta, which will then minimize this effective energy or minimize some free energy, depending on what you're thinking about, in the presence of some electromagnetic field, which will also adjust itself to minimize things. But all right. So, but this is our minimal theory for a superconductor. When I'm doing electrodynamics for a superconductor, I have to add this term, basically, because rho sub s is non-zero. Any questions? All right. So, I mean, these are all, quite subtle and deep arguments, and it took the community many, many years to get them right. But once they're formulated in the right way, they hopefully look kind of obvious. And but they're very, they have a lot of depth in them, and it took a while to find the right language to say this. Okay. All right. So now let's proceed and try to write down what are the consequences of this particular term in the Freener of the Hamiltonian.
Subir?
Yes.
Is there any restriction on dimension here? I guess it should be greater than 2, right?
Well, formally, the arguments are correct anywhere. But in low dimensions, you could just say rho sub s is 0. So if you're in 1D, at finite temperature, then rho sub s is 0 at all temperatures. In 2D, in fact, this argument is true even at finite temperature as long as you're below the costless-Thouless transition. Because even though that's the unique case in 2-dimension at finite temperature, where even though there is no long-range order, there is still a helicity modulus that's non-zero. Yeah, but we are not going to discuss that here. That's more for, I think we discussed that last semester a little bit. Right, so formally this is true in any dimension. You just have to ask, is rho sub s non-zero or not?
That makes sense. And it's greater with higher dimension, or?
Yeah, it's more likely that there's a wide temperature range where rho sub s is non-zero in higher dimension.
That makes sense. Thank you.
Okay, so now let's look at some physical quantity. You can't measure theta, we can measure magnetic field. But another thing we can measure is the current. So can we compute the current from this? Okay, you can do it again in general gauge, but from now on, I'm going to fix the gauge. This will del dot A equals 0. Okay, when del dot A equals 0, you can just expand out this term. You can square this and square this, but the cross term is 0 because you can integrate by parts and then use this and see that the cross term is 0. Okay, well, that's just an aside. But in any gauge, in principle, you can compute the physical electromagnetic current by just taking the functional derivative of your effective Hamiltonian with respect to the external vector potential. So the proof of this is that it's true for the microscopic Hamiltonian. If you just write down the microscopic expression for the current that you know, and just take the derivative with respect to the vector potential, you get of the Hamiltonian with respect to the vector potential, you get the current. So it should be true here since it's true at the microscopic level. So now I have a effective Hamiltonian. I just have to take the functional derivative. And I take this derivative by using this fact that just simplifies life a little bit. In fact, historically, London obeying this equation without having this argument and without even understanding the correction to broken symmetry or to gauge invariance. Well, maybe he did, but he didn't say it in the words that I've said it. Okay, so you have this thing squared, but you want this functional derivative, so that term doesn't even matter in this gauge. And that's really the beauty of this gauge. You can even forget about theta at the end. In other gauges, you can't. And so there's only a squared term here. So you take the derivative of that, and you get a very simple equation. That's the famous London equation. J is a constant, which depends on rho sub s times A. Now, when you first see this equation, and I'm sure that was the reaction of many people after London wrote it down, they said, well, that doesn't make any sense. The left-hand side is a gauge invariant quantity. The right-hand side is not a gauge invariant quantity. Yeah, true enough. To make it gauge invariant, you have to work a bit harder, but we are going to restrict ourselves to this gauge because for now, looking at time-independent phenomena. And in that gauge, you can see why that gauge is needed, because if you have time-independent phenomena, you want the divergence of J to be 0, just to conserve particle number. And naturally, that's satisfied. So that's why you need this gauge to use this equation. If you're using this equation without this gauge, you'll run into problems because this is not true. And this is always true. There's no choice there because J is a gauge invariant quantity, at least for U1 gauge symmetry. All right, so this is the famous London equation, whose coefficient is just given by this helicity modulus and then fundamental constants of nature that we know presumably very well. Okay, and just from this London equation, we can now derive the two basic properties of a superconductor. First, we can get superconductivity, at least at some level, but you have to think about it a bit more carefully. Just take the derivative of the two sides. So now we have derived it for time-independent phenomena, but let's imagine time is varying very slowly. then the equation you would get is the dj dt is some constant times the electric field. Of course, the electric field is dA dt in this case, minus 1 over c dA dt. So you get this result. And that actually, you can see, what is that equation? Well, that's nothing but Newton's equation, if I don't worry too much about the coefficient. Newton's equation is acceleration, mass times acceleration. This is our dv dt is equal to the force, which is the electric field times the electric charge. So this is essentially Newton's equation of motion, telling you that the current increases when you apply a magnetic field, so charges accelerate. So this means really, so what happens in a superconductor, that can't happen. So the electric field will be zero, but current can still flow. So there is no dissipation. It's not Ohm's law. It just tells you charges accelerate if you had an electric field in a superconductor. Now, before you get too excited and say, oh, I've explained superconductivity, you have to pause a bit, because this equation is actually also true in the Jellium model, or the free electron gas, or even the interacting electron gas. Even actually in a lattice is true, but does not go there. It's some equation like this is true in what we call a perfect metal. And the reason is that, well, even a Jellium model, if you apply an electric field, there may be a lot of collisions. But if you have a perfect lattice, just the center of mass of the Jellium of the Fermi sphere will just respond to the external electric field. All the interactions don't matter because they don't couple the center of mass. And so the whole system will just move and accelerate in response to an electric field. So just getting this relation in general is not a victory. But what is a victory is that you can now argue based on, in fact, if you go back to our arguments here, nowhere did we assume there were no impurities or there wasn't a lattice. It was just an argument associated with a broken symmetry. You could put in impurities. You can, even make things non-translational invariant. You can even make rho sub s slightly a function of r if you want a little bit and put it inside. Could be different in this part of the sample, that part of the sample. You can go through all of those arguments. Everything I presented didn't really use translation invariant in any fundamental way. And so the fact is that this equation holds even in an inhomogeneous sample with any number of impurities, sorry, this one. And that's why it's a superconductor. So what you've shown is that there's acceleration of charges even in the presence of imperfections. And that's not true for the Jellium model. Then that won't work. So, but that's a hard calculation. Anyway, so that's the key point. This explains superconductivity. The London equation explains superconductivity, because it's very generally true, even in the presence of inhomogeneities. So that's the first result. And the second result is I can now get the Meissner effect, just again from the London equation. So how do we get it? Well, first you take Maxwell's equation, which is curl, or Ampere's equation, I guess. Curl B is, again, forgive me, but CGS units here, 4 pi over C times J. Okay, so now, I have one equation between B and J, and I have this other equation. And now I can reduce them to the same equation, one for either for J or for A. So this equation is the same as del cross B, del cross A is equal to this. But in the London gauge, this is just minus del squared A, basically. And then, so what do you do? Okay, I've written it. All right, so I guess you have to do some vector algebra, which is not immediately obvious to me. I guess what you want to do is take yeah, so you want to take this equation here and do a del cross both sides, and then use which is Ampere's law. This equation, okay, there's some simple vector algebra, excuse me, running out of time. You will get this equation. So this equation here is for the magnetic field, and there's a similar equation for the current, obviously. So now we're talking about gauge invariant quantity. And so this is the Laplacian squared of the field. And so this better have the units of 1 over length squared. So that's why we call it 1 over lambda L. Lambda L has units of length. And it's called the London penetration depth for a reason that'll become clear in a minute. And that 2 is, of course, obviously in the wrong place. 2 should be here. So 1 over lambda L squared is equal to this. So now we have an equation for the magnetic field, which we can measure, which involves this lambda L. So presumably I can measure lambda L. And lambda L is related to this mysterious helicity modulus times some h bars and e's and c's. These are fundamental constants of nature. So this is a very, very useful relation because the lambda L then, if you measure it, is a direct measure of rho s. So if you measure lambda L, units of length in your lab, you know rho s in units of energy times length to the d minus 2. No questions asked. This algebra here is for 3 dimensions, and so of course you have to make some modification in other dimensions. Okay. Now this equation, it basically explains the central property of a superconductor, which is the Meissner effect. So what you do now is you take a geometry like this. So you take, this is your, what was the direction I used? X, yeah. So this is going to call X in this direction. Sorry. And then the vertical direction will be Z. Yeah, so this will be Z. Then you have a boundary. And here you have a superconductor. In the positive, this is X equals 0, is the boundary. And here you have free space. And you come in with some set of magnets, and you apply a magnetic field pointing in the Z direction, B naught over here. So here, this is free space, and B naught is just a constant. All right. And so now we want to solve these equations that I have here, the London equation and Maxwell's equations, and then you have to match boundary conditions and so on and so forth, which I'm sure you can do very easily. And this equation turns out to be a very simple solution. It just has exponential decay. So you find over here that B on this side in the superconductor is B naught in the Z hat direction, X minus X over lambda L. So the tangential component of the B field has to be continuous. That's something hopefully you remember from your E&M. So B naught has to be continuous across the boundary, and therefore the only solution. So this equation, of course, this only applies inside the superconductor. I can't use this equation in free space. Effectively, lambda L is infinity in free space. But it's finite inside the superconductor, and therefore my magnetic field decays to 0 in a length which is lambda L. So it just quickly decay to 0 in a length which is lambda L. And after that, that's why it's called the London penetration depth, because the magnetic field penetrates a distance lambda L into the superconductor. What about the current? Well, the current you can just work out just by, again, this equation. Once you know B, you can work out the current. So the current is also non-zero, and it's going to be, its points here, as you can see, in the y hat direction. So the current is going into the plane of the screen. Let's pick another color. So the current is a surface current, which we call a supercurrent. And it's only right on the surface of a depth lambda L. So this is J sub S. So that's, and that J sub S is present right on the surface of a superconductor. So what you have the situation, if I put a superconductor in a magnetic field, what it does is it sets up on its surface a supercurrent in the depth lambda L. And that current, magnetic field is constant, just sitting there. And that current flows forever. It's a persistent, flows forever on the surface of the superconductor. That's the supercurrent. And it's carefully, of course, the system chooses the current in exactly the right way so that the net field, that's one way to think about it, inside the superconductor is completely canceled, which is kind of like Lenz's law. So you bring in you have some big coil outside, which creates a magnetic field everywhere inside. When you stick in a superconductor, the superconductor puts in currents inside in the opposite orientation so that right inside the superconductor, the supercurrents will cancel the field that was created by your big coil. Okay, so that's what it might take a while for the superconductor to do this, but in equilibrium, this is what it wants to do. If this is the lowest energy state, where it will have persistent currents on its surface, so that there's no magnetic field inside. Okay, yeah, so that's really the essence of superconductivity, the Meissner effect, and the appearance of persistent currents on its surface in the presence of a magnetic field. Questions? All right, great. So I'll have our discussion session tonight at 9 p.m. We can continue to discuss some of this. And on Friday, we're going to do the Landau-Ginzburg theory, and that will, I think, be the last lecture on superconductivity. We should move on to, well, no, the next week we'll talk about high TC superconductivity. Okay, so there's more to do. All right, thank you very much.